Hi, I'm Sean Carroll. I'm a theoretical physicist here at the California Institute of Technology. I've been challenged to explain dimensions to 5 different levels. The idea of a dimension sometimes in pop culture is misunderstood, like there's an extra place you can go, a mystical dimension or something like that. To a physicist or a mathematician, a dimension is just the direction you can go in, up, down, left, right, forward, backward. To you and me, we think there's 3 dimensions around us, but then physicists start talking about extra dimensions. How can you hide them? Where might they be? I'm hopeful that we'll learn something at each level. We're going to talk about some science. Do you like science?
Yes, a lot.
Oh, very good. You come to the right place. So we're going to think about physics. Have you heard the word physics before? Do you know what that is?
Yeah, kind of.
Well, what's your idea what physics is?
I'm not so sure.
Okay, I just think of physics as, the study of everything. What stuff is, what stuff does. So today we're going to talk about space, and in particular the idea of dimensions. Have you heard about dimensions?
At the camp, I'm in a 3D printing one.
3D printing, good.
So I don't choose the size. All I have to do is the shape.
But do you know what 3D means?
It's 3-dimensional.
3-dimensional, as opposed to what is ordinary printing?
So ordinary printing would be 2D.
What do you say when something is 1-dimensional? What's an example of something that's 1-dimensional?
I think 1-dimensional might be a circle, I guess, or maybe a line.
A line is the
Yeah,
perfect
line.
example because it's one thing that's straight, right? So here's some toys. We're going to build some dimensions, right? So what would you say about this?
That's 1-dimensional.
Exactly. It's not really 1-dimensional, right?
So everything has to be 1 or 2-dimensional before it's 3-dimensional.
And how would you find yourself? Like if someone said, "Where are you?" Like could you use some words or ideas to say where you are on that line?
I think I would be maybe there since I'm facing it.
But here's what I want you to think about. If I say I'm at this point on the line, I could translate that into saying I'm at the 3-centimeter point. If I were here, I'd be at the 4-centimeter point, the 5-centimeter point, right?
Yeah.
So every point, every location on our little line
Has its own unit.
has one number.
Yeah.
We need one number to tell you where we are. That's 1 dimension. That's what it means to be 1-dimensional. I only need to tell you one number to figure out where we are.
Unlike 3-dimensional, you have to tell a lot because if it's like a sphere, you kind of have to start using points.
There you go, exactly. We're going to build a little 2-dimensional space. You want to do it? You want to do the honors here? Why don't you put those 2 lines together?
If you make it 2-dimensional, is this a corner?
Exactly.
Another way is if you have this space in between is an angle.
I think you should be in this chair and you should be explaining this to me. You're much better than this than I am.
Yeah.
So those are the dimensions. That's how we think about dimensions. Remember, we just needed one number to find ourselves on the line. We need 2 numbers to find ourselves on the plane.
I think that would be an X or Y-axis.
There you go. So do you think we could have more than 3 dimensions?
3D is the maximum of dimensions for shapes.
Well, as far as we know. This is why physicists think about things we don't know about. We're wondering whether there could be extra dimensions you've never seen that are tinier than atoms. So what have you learned? What do you know about dimensions now? How do you think about dimensions in a slightly different way than you did before?
So at least everything has a certain dimension.
Yeah, do you think you'd be excited if physicists said that they found extra dimensions of space?
That would be amazing discovery. The news would be spreaded around the world rapidly.
I think so. I think you're right. All right, Hank, we want you to, keep up studying, learn a lot of math and physics, and help us discover new dimensions someday. Does that sound like a fun idea?
Yeah.
Do you like science? Is that something you think about? What kind of science?
I like biology and computer science.
All right, you're in the wrong place. We're not going to be talking about biology, computer science. So we want to talk about the idea of dimensions. Do you know what a dimension is? How you would define dimensions?
I guess, I don't know how to exactly define it, but I know the first floor.
Right, you know the difference between 1 dimension, 2 dimensions, 3 dimensions, etc. So let's do a little experiment here. So there's 1 dimension, I'll give that to you. Now here's your task. I'm going to give you another dimension, and I'm going to ask, hold those 2 things at right angles to each other. It's easy to do. Yeah, there's no tricks here. I'm not trying to fool you here. Okay. Now, this is going to be slightly trickier. I'm going to give you this. I want you to hold all three of them at right angles to all the others at the same time. There you go. So what that's doing is when you had just two, that was describing a two-dimensional plane, right?
Yeah.
Like the two things pick out a plane, the three things pick out all three-dimensional space. Now I'm going to give you one more, and I'm going to ask you to hold that fourth one so that it's at a right angle to all of the other three at the same time. All right, now I am tricking you. It can't be done, right? You can't do it. So we just experimentally proved that space is three-dimensional. That's sort of what it means to be three-dimensional, that there are three different directions you can move in, and there's not 4 or 5 or 6 directions you can move in.
Oh, okay.
There you go, three-dimensional space, right? Mm-hmm. So have you thought about using coordinates in 3 dimensions?
Yeah, I was actually doing SAT prep.
There you go.
It showed like the X, Y, and Z axis as well.
That's right. So that's exactly what these would be. Have you heard that there are other coordinate systems other than X, Y, Z?
No.
But we could also say how far we are away from the center, just the distance, and then the angle that our little line makes with, let's say, the x-axis.
Yeah.
So that's a different way of giving you two numbers and locating yourself, and we call those polar coordinates. It's a different coordinate system. What we want to do as physicists is look for extra dimensions. Can you think of any way that there could be extra dimensions?
Time?
Time. Yes, Einstein said that we can think of time as a fourth dimension, and that's a very fascinating thing that we could talk about all by itself. But what about space? What about the solar system? Like if you wanted to tell me where a certain star was in the sky, do you know how we do that?
I have no idea.
It's exactly the same thing as latitude and longitude, but we put coordinates on the sky. Oh. So astronomers call them right ascension and declination, which are two terrible words, but basically you've seen, on the globe where you draw latitude and longitude, what it looks like, sort of the peels of an orange kind of thing, right?
Yeah.
So you can define something as well, how high above a certain location on Earth it is, but the Earth is rotating and revolving around the sun, so we have to define separate celestial coordinates.
So there's like how many dimensions would there be?
We don't know. The optimistic view is that there are 6, but the thing is, some of them might be really, 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 really small, like way too small for us to ever see.
Yeah.
And some of them might be medium-sized that hopefully we can see.
Oh, okay. So since it's all theoretical, like this could not be 3 dimensions.
Absolutely right. And this is sort of the state of uncertainty that physicists are stuck living in. Honestly, out there, if you go out onto campus and talk to the physicists, half of them will say probably extra dimensions exist, and half of them say, no, that's just nonsense. We really don't know.
Yeah.
Okay, after all this,
yeah,
someone comes up to you on the street and says, what's a dimension?
Oh man, I guess what I've learned today is just that there are not just 3 dimensions, or at least we think. Everything's theoretical. It's all just really kind of confusing.
That's right, and if they're still bugging you, you can just give them some sticks and ask them to put them together, and that would shut them up.
Yeah.
Where do you go to school, and what do you study?
I'm going to be a sophomore at Pomona College, and I study math and physics.
Oh, math and physics. Yeah. Okay. What kind of physicist do you want to be? Do you know?
I really don't know. I like theory and experimental, so it's kind of tough for me to say.
Usually, if it's math and physics, you end up as a theoretical physicist, right?
Yeah.
Not an experimental one. So our theme here today is dimensions. Mm-hmm. So this is great that you have some math background, because mathematicians think about dimensions in a different way.
Hopefully, yeah.
So how would you explain to, your friends who are not math and physics majors, what is a dimension yourself?
My first intuitive thought is, what are the coordinates,
Mm-hmm.
So if we were looking at things, if we're looking at a dot, that's one, or a line rather, that's one-dimensional because we can only measure it one way. But then if we look at a square, then we're increasing like that. So it's all, basically what coordinates we can use to measure something in.
That's exactly right. And so you've heard of space-time being 4-dimensional, right? Mm-hmm. Now, in some sense, that's kind of trivial to you and me because, of course, you have space, which is 3-dimensional. You have time, which is 1-dimensional. So space-time is 4-dimensional. But it didn't occur to anyone that was a sensible way to talk until really relativity. This is the crucial thing, right? Is that what Einstein realized is that, sure, there's both time and space, but how we divide space-time into time and space can be different for different people. And really, there's a real sense in which four-dimensional space-time is kind of a generalization of three-dimensional space. And I think to really explain this, we're going to need a blackboard.
Okay.
Let's bring one in. All right, the thing about relativity is that they really want you to think of space-time as one four-dimensional thing, right? It's kind of like space. It's not just 3 dimensions of space and 1 dimension of time.
Why though?
Why? This is a very good question. So let's just start with space, right? We know a little bit about space. So here's my simple-minded way of drawing space. 2 dimensions, because that's how many I can draw on the blackboard. Let's say X and Y. And what is special about space? There's many things, but one is that if I have, a curve or a path between 2 points, there's a distance that you can calculate, right? And the distance between those 2 points doesn't depend on your coordinates. It doesn't depend on whether you're in radial coordinates or Cartesian coordinates or whatever. I'm allowed to imagine a curve that does something like this between those 2 points. And if I were a person walking on that curve, I would have an odometer with me maybe, and I would know, you would know, even without having done that, this path is always going to be longer than that path. There's a formula, Pythagoras' theorem. It tells you what the shortest distance path is. That's the point. The physicalness of what is real is the distance along a certain curve. So space-time is like that. That's why it is useful to think about space-time. So let me draw space-time. Here's how we usually draw it. I'll just say X, but all of space is condensed to this one direction, and this is time. Okay, so if you're a little person, you start at some event. So you're located somewhere in space, somewhere in the 3 coordinates of space, and whether you like it or not, you're moving through space-time just by getting older. When people ask me, can you travel through time? I say, yes. Yesterday I traveled 24 hours into the future, and here I am, a day later. So that's just this. Okay, you're moving through time like it or not. So what Einstein says is, look, I can travel through space-time in different ways. Like I could hop in a rocket ship and fly out and then fly back. And then I could meet you there. So this is a different trajectory through space-time, right?
Yeah.
And it's almost exactly like the space story. The space story says there's a distance is different along different curves. Einstein says there's something that measures the length of these curves, and we call it the proper time. It is literally the time that you would read on your wristwatch.
So it's kind of like our fundamental time, like our base time?
Well, kind of. What Einstein wants to get across is there's no such thing as fundamental. Like there's the universe's time, this big letter T that might tell you how old the universe is, but then every individual has a clock with them, and they measure their own time depending on how they're moving through the universe.
I see.
And the crucial difference is the time is not the same for this person who stayed behind and sat in their chair and this person who zoomed out there.
Why is that this one's shorter then?
There is what we call a metric on space-time. And when we talk about Euclidean space versus a curved space versus a sphere or something, that's a different metric. And space-time has its own metric, which says the following thing, that the path between 2 events in space-time that is a straight line will always be the longest time.
I see. Oh, okay.
That's the difference.
All right.
So when Einstein had this idea, gravity could be related to the curvature of space-time, he needed some equations. Okay, so he got it. That's a long story. We'll put that aside. What he figured out was that rather than gravity living on top of space-time, it's a manifestation of the curvature of space-time. So when you have the Earth, the Sun, the Moon, they cause a gravitational field. They're actually warping the space-time around them. They're giving it a different geometry.
Would it be if I had a spring, or not a spring, but like a sheet, and I dropped a book in the sheet, curves down?
Yeah, exactly. If you had a sheet that was originally flat, and you send a marble on it, it would go in a straight line. But then if you put something on it so it warps it, that marble is now going to be deflected.
I see.
Einstein says that gravity is just like that.
I see.
But there are no straight lines because space-time itself is curved. So do you think if you had to explain relativity, what would you say?
I think I would go with the train paradox. Let's say I'm stationary and someone's moving past me on the train. They think they're stationary on the train. They think that they're not accelerating. But if they start walking through the train cars, then they are accelerating in their frame. But then from my outside frame, where I'm completely removed, I see they are accelerating. So I guess that relativity is all about perspective, I guess, in a way.
Yeah, that's right. And it goes exactly back to what we drew on the board, where how those two people in the train and on the ground would divide space-time up differently into space and time.
That was pretty good. I learned a lot.
It's a lot of fun stuff to talk about. So observational cosmology, so like what do you look at?
So I work on 2 ground-based surveys in the optical, and we're basically trying to make huge maps of the universe so that we can study dark energy.
I'm sure you've heard about extra dimensions a little bit.
I've heard it, yeah.
Well, I'm thinking about the idea that there might be more than 3 dimensions of space. What is your impression of theoretical physicists who think about things like extra dimensions of space that they haven't ever seen?
I get a little scared because I think how can you prove these theories, right? One theory I've heard of, I don't know if this fits in with that, is bubble universes. Is that an extra dimension? Does that fit into that, or is that something?
It does. In fact, one way that different universes might sort of be created and be different from each other is that different universes could have effectively different numbers of dimensions. Like we have 3 dimensions around us, but there's people out there, aliens, who could live in 5-dimensional universes.
And are each of those dimensions, are they governed by the same laws of physics, or is there like a separate Lagrangian for each universe, or how does that work?
We think that it would be, all of this is incredibly speculative and we don't know for sure. But the idea is that there is some deep down underlying laws that are universal and the same, but they show up differently, so they appear different. So the specific particles and forces and masses would be completely different in different parts of the multiverse.
Okay.
Why in the world would you think that there are extra dimensions, right? So you've heard of string theory?
I have. So the string theory is basically a theory of quantum gravity.
So we have quantum mechanics, right? The theory of atoms and so forth and how those work. And then we have gravity, and gravity doesn't seem to fit in. It's the one force of nature that we can't really easily fit into this quantum mechanical framework. So string theory is one of the best ideas. That's the good news. The bad news is that it only seems to work if space-time is 10-dimensional. So you would say, well, then it's wrong. It can't be right. Space-time is not 10-dimensional. Space-time is 4-dimensional. We've observed that. But instead, we say, if space-time looks 4-dimensional to us, but string theory, which might be the best theory we have of quantum gravity, says it must be 10-dimensional, maybe we can hide those extra 6 dimensions somehow. So here's how we could get lucky. We could imagine that there are extra dimensions of space that are curled up somehow, that are so small that we can't see them. This is actually an old idea. It goes back to Kaluza and Klein right after general relativity was invented in 1915. But there's a more recent idea that says there could actually be relatively large extra dimensions. There could be extra dimensions that are actually that big, like 1 millimeter across, that you would not have noticed. But here's the new exciting idea. So let's imagine, okay, this is a piece of paper, but let's imagine this is our entire world. So in other words, our real world is 3-dimensional, but let's imagine that we're just idealizing it down to 2 dimensions. So we all live here, you and I live here. But let's imagine that we're embedded in this bigger space. So there are extra dimensions that are actually big. Okay, let's imagine that. When I say we live on this 3-dimensional world, what I mean is imagine that the particles that you and I are made of, right, the quarks, the leptons, the electrons and everything, all the forces we know about, electromagnetism, the weak nuclear force, the strong nuclear force, imagine that they can't leave this surface. This is what we call a brane, B-R-A-N-E. Have you heard this word before,
I've
right?
Heard, yeah.
Do you know where it comes from?
No.
From membranes. We have lines, 1 dimension. We have 2-dimensional surfaces. So if you have a line that is a vibrating physical thing, you call it a string. Right?
Right.
If you have a 2-dimensional surface that vibrates and is a physical thing, we call that a membrane. Membrane theory goes back. It never was as popular as string theory, but it's been around for a while. But if you have extra dimensions of space, then you can have 3-dimensional vibrating things and 4-dimensional vibrating things.
So how do these strings give rise to things like mass and charge and basically give us the properties of the particles we see?
Well, basically, the strings are the particles that we see. It's exactly the same thing as we said, for the straw. If you look at it far away, it looks 1-dimensional. A little loop of string, so a little 1-dimensional circle that is vibrating, if you look at it from very, very far away, it just looks like a particle. So in string theory, an electron is a little string. A photon is a little string.
So is string theory part of what they call the grand unified theory? Is it supposed to be the last thing that sort of unifies all the forces together?
Yeah, string theory is even better. So the phrase grand unified theory was coined in the 1970s for theories that joined electricity and magnetism. So a good string theory is gravity plus a grand unified theory.
Okay.
It's even better. It's the theory of everything. What would you tell a friend of yours if they asked you what dimensions are, what extra dimensions are, what a brane is?
So we have 3 spatial dimensions. A brane is sort of the next level. So a brane is a higher dimensional object that vibrates through space.
That's right, and we could live there. The world we see around us, the 3 dimensions of space around us, could reflect the fact that we are somehow stuck on a 3-dimensional brane trying to escape.
It was really cool to learn about strings and branes and how looking at gravity on small scales is actually connected to what I do in looking at gravity on these cosmological scales. And it's definitely something I'm going to think about in my research.
You're a string theorist, so tell us what kind of string theory you do, what it means to be a string theorist.
One of the things that's key in the whole story of string theory is the piece of it that talks about quantum theories of gravity. So I'm very excited about what happens to space-time, what does it even mean at the quantum level.
Cool, so do you think a lot about extra dimensions in your everyday life?
Yes, I do.
And so when you think about extra dimensions, you put them together with branes and different fields wrapping around the extra dimensions and so forth, right?
Yes.
You know, a lot of people, a lot of string theorists, they care a lot about all of the different ways in which we could hide the extra dimensions. As someone who cares about cosmology, I want to start asking, why are the extra dimensions small at all? How did that happen? Is this something you think about yourself?
Yes, well, ultimately we'd like to understand the observable universe. If string theory turns out to be the thing that the universe cares about, we'd like to know, with all of these possibilities that are in string theory, how do we get the one that looks like the world we live in?
The thing I want to talk about is this paper I wrote with Matt Johnson and Lisa Randall, where we realized there's another way to compactify extra dimensions spontaneously, dynamically. If you imagine starting with this big piece of paper, you couldn't wrap up everything, but within some region of space, you could make a tube.
Okay.
Right?
Okay.
And down there in the tube, it looks like you're a long thing that is compactified in one direction and infinitely extend in the other direction. So there's one less macroscopic dimension of space.
Okay, that's
Think
nice.
that sounds plausible to you?
It sounds like fun. What I would immediately ask is whether the large dimensions come from in the first place. Is that something you address, or you just assume that all the dimensions are large as a starting point?
Yeah, so we certainly assume that they're all large as a starting point, and it's worse than that. So in our paper, we imagine you start in de Sitter space. You start in a universe with no matter, no anything like that, just empty space, but with an energy that is positive, and all the dimensions are large.
But where did they come from?
It was always there.
Why?
Why not?
Okay.
Well, I think that this is a good, again, this
So you're
is,
replacing one prejudice with a different prejudice.
I would say that we shouldn't be prejudiced one way or the other.
Just a large, 10 or 11 dimensions with a cosmological constant doesn't seem like a fundamental starting point. It sounds like there needs to be something to underlie that. But it's a fun scenario.
Yeah, so let me tell you a little bit more about the scenario. So there are black holes. Good, right?
I've heard of them.
There are black branes as well.
Indeed.
Why don't you explain to us what a black brane is?
Well, in some ways, it's very much like a black hole in that you have far away from it, you have these large, just flat dimensions. As you move in, there's something in the interior. It has itself higher dimensions. And so, because physicists love to joke, they thought, well, it's like a membrane, but it can have many different dimensions. Let's use P to stand in for those number of dimensions, and so they call them P-branes.
Yeah, I've been trying to explain that to lower levels, and they always look at me like, are you pulling my leg here a little bit, or is this the real thing that they use? Yes, it is the real thing they use. We study these branes in de Sitter space, and so what we found is that there are black brane solutions which, instead of having a singularity inside, are non-singular and stable and compactified. Is this a familiar thing? I know things like this have been discussed, right?
Yeah. So a lot of the branes that are relevant for studying things to do with anti-de Sitter spacetimes in various dimensions actually start out as these non-singular type branes, and then you find in the core there's actually an anti-de Sitter spacetime.
Right. Imagine that rather than going down to a point, it just asymptotes to some fixed radius that continues infinitely far down there. But then you can ask, okay, what about the rest of the universe? You have some sphere, some 2 dimensions compactified, and the balance between the cosmological constant and the electromagnetic field keeps it at a fixed distance.
Good.
But then the other dimensions, the transverse dimensions, don't need to be anti-de Sitter. They can have either positive, zero, or negative cosmological constant. So you can basically get any sort of cosmological solution times a compactified sphere.
Is it that these have the lowest action of all the things that could possibly, all the possible solutions?
I guess, I mean, maybe you think otherwise, again, or maybe you could change my mind. I think that as long as it can happen, it will happen some of the time, right?
Okay,
I mean,
that's fair.
it's one of the things that could happen. So, I mean, obviously, we know
It's
that once
quantum, baby.
it's quantum. If it's allowed, it's going to happen.
I stole that from Keanu Reeves, I'm afraid.
Someone probably wrote it for him. So it's possible that if you do have this starting point of an empty de Sitter space with positive cosmological constants and fields lying around, you inevitably get a multiverse. It just happens, It's just part of quantum nucleation into different things. And then maybe you need to explain why we live in this universe rather than some other one via the anthropic principle or something like that. So how does our kind of, low-tech, old-fashioned way of making new universes intersect with the kinds of things you think about?
Well, it's interesting because there's a lot of activity going on inspired by things we learned from working in anti-de Sitter space, where the cosmological constant has the wrong sign. So you will find that there are a number of papers, as many of which you've probably you've read more of them than I have, which try then to take different kinds of branes, these extended solutions, and there are many different kinds doing different things. We understand them well enough now that we can put them together in various ways. They intersect, they dissolve inside each other, they wrap each other, they overlap, and you do them all in all sorts of different ways and show that you can construct four-dimensional universes with a cosmological constant of your desire, depending upon how you did the construction.
I know not everyone buys that.
Not everyone buys that. There's a big discussion in the literature right now.
And if we put aside for the second the concerns of our colleagues in other parts of physics, and it's just amongst us chickens, what do you think about the future of cosmology and string theory and the dynamics of these extra dimensions?
I think it's going to get way more interesting than we're currently able to grapple with right now. And I think there are hints of it. There could be a description of the physics that might be our early universe that is like that molecular description. And then from that emerges flat spacetimes, maybe four, maybe some mechanism tells you it's four and not something else. I think that's where we're going.
If the viewers want to know more about how space-time can emerge from quantum mechanics, they could read the graphic novel you just wrote.
Right, yes, I wrote into a graphic novel called The Dialogues, Conversations About the Nature of the Universe.
And I just wrote a book called Something Deeply Hidden about many worlds, quantum mechanics, and how space-time can emerge from it. Plenty of reading material for the audience out there.
Excellent.
So that was fun. I hope that everyone did learn something. I know that I did. It was very nice to see how the idea of dimensions and space resonates in different ways with different people, all the way up to talking to Clifford about the forefront of modern research. I really do think that we're not done understanding how dimensions work. There are 3 dimensions of space. Why that? Why not 2? Why not 27? I think that we really don't yet have the data or ideas to think about this, but we're creeping up on it. I'm optimistic about progress in the near future.
I'm a professor at the University of Waterloo.
And I'm a sleep scientist at UCSF.
Today I've been challenged to explain lasers.
To explain the topic of sleep at 5 different levels.